All right, today we're going to be talking about symmetry. So if you can get your table of contents down, we will proceed shortly with our notes. Just a reminder that your test is next Wednesday, so we're going to be going over symmetry today. And then the next two classes, Friday and Monday, we're going to be talking about composition of transformations, so performing two or more transformations at once. That'll be Friday and Monday. And then next Tuesday we'll review, and Wednesday will be your test. The quiz grades are in. I will get those back to you when I come back tomorrow, but if you would like to check your quiz grade, you can in Skyward, sorry. So let's first talk about what symmetry is. You've probably heard the word symmetry before, so it's not completely foreign to you, but a figure has symmetry if a rigid motion can map the figure onto itself. So we've talked about three different types of rigid motion so far. Reflection. Well, I guess I should say it in the tense that it's written here. You can check to see if it can be reflected, translated, or rotated onto itself. If any of those three things can be done to the figure and it still remains on top of itself, it has symmetry. So we're going to be talking about three different types of symmetry today, but in this first example, we're just going to talk about all three types. So in this first example, what transformations can be used to map the figure onto itself? Think about what line or where you could fold this crazy shape so that it would land on itself. For example, if I folded directly down the center, it would land on itself. So if you reflected the image over that vertical line through the center, it would land on itself. So if we were describing that, we can say a reflection over a vertical line through the center. That's one way the shape would experience symmetry. Take a look and see if you can draw another line where you could fold that shape and it would land completely on top of itself. Maybe you came up with this line right here. That is a reflection over a horizontal line through the center. There's one more rigid motion that would land this figure completely on top of itself, and that's a type of rotation. So imagine that we put a point right at the center. If you rotated this image 180 degrees, it would still land completely on top of itself. So a rotation, 180 degrees around center point. For the rest of the notes, we're going to divide it into two types of symmetry: reflectional symmetry, and on the back you'll see rotational symmetry. Reflectional symmetry is when it's also referred to as line symmetry. It's a symmetry for which a reflection over a line maps the figure onto itself. So your blank here, reflectional, or just in parentheses, put line symmetry, is a symmetry for which a reflection maps the figure onto itself. So if we were trying to describe what type of reflectional symmetry this shape has, there's two lines that can be drawn where the figure, if it was folded along that line or reflected along that line, would land on itself. We have a vertical line through the center. I should say reflection over the vertical line through the center. Or try to find the other line that this could be folded on. We also come up with this horizontal line through the center. So that one has 2 lines of reflection. Now this one is another one that has rotational, like you could rotate it around the center point, but since we're focusing on reflectional symmetry now, we're not going to dig into that until the back side. But this one has 2 lines of reflection. Take a look at this smiley face. See if this smiley face drawing has any lines of reflection, or see if it has any reflectional symmetry. Is there any way you could fold that smiley face so that it would land completely on top of itself? Should have found this center line so it can be reflected over a vertical line through the center. Because of the way this smiley face is, there's no other lines that we could fold this smiley face on so that it would fold onto itself or reflect onto itself. So it just has 1 line of reflection. In our last example, see if you can find the line or lines of reflection for this image. This one you could reflect over the horizontal line through the center. So it has 1 line of reflection. Moving on down to example 3, when we're talking about line symmetry or reflectional symmetry, this problem is asking us to find how many lines of symmetry does this regular hexagon have. When it says regular hexagon, that just means that all the sides and angles are congruent to each other. So I want y'all to just take a moment and see if you can find some of the lines of reflection, or all of them, for this hexagon here. You can find some going through the vertices of the hexagon. So if you folded the hexagon on that line, it would fold onto itself or reflect onto itself along this line, along that line. All of those lines go through the angles of the hexagon or through the vertices. So that accounts for 3 of them. And then you could also go through the midpoint of each of the sides. So if you folded it right down the center, that's another line of reflection. Could have folded it through those 2 midpoints. And again, here. So that accounts for 6 lines of reflection for that regular hexagon. In these last examples, we're just finding how many lines of symmetry each of these shapes has. So let's start out with this rectangle. Figure out how many lines you could fold this rectangle on so that it reflects onto itself. If you folded it on the vertical line through the center, that's 1. If you fold it on the horizontal line through the center, that's another. You can't go through the vertices. In other words, you cannot go right here, because if you folded it along that line, it would not land on top of itself, nor through the other corner of the rectangle. So there's just 2 lines of symmetry. Check out the trapezoid. How many lines of symmetry does this trapezoid have? Hopefully you came up with 1, just this vertical line through the center. You cannot do this horizontal line through the center because these corners would not match up with each other if you folded it down. So just one line of reflection. Check out this trapezoid. Are there any lines we could fold that trapezoid on so that it lands completely on top of itself? Correct answer is no. There are 0 lines of reflection. And the last one, where is the line of symmetry that we could reflect this shape on so that it would land on top of itself? It's one line of symmetry is right here. That's the only place you could fold that L shape so that it lands completely on top of itself. So 1. That's reflectional symmetry, or also known as line symmetry. Flip it onto the back and we're going to talk about rotational symmetry. A figure has rotational symmetry if its image is mapped onto the pre-image after a rotation of less than 360. So it shouldn't say less that. It should say less than 360. If it's rotated 360 degrees, it's of course going to rotate onto itself because that's like just a full circle. But if it can rotate less than 360 degrees and still land on top of itself, then it has rotational symmetry. So a figure has rotational symmetry if it can rotate less than 360 degrees and land on top of itself. When a rotation of specifically 180 degrees maps a figure onto itself, it's called point symmetry. So it's just a special type of rotational symmetry. In these first few examples, all of these shapes are going to have some sort of rotational symmetry, and we're going to try to figure out how many degrees do we need to turn it so that it would land on itself. Starting out with this equilateral triangle. Just a reminder that an equilateral triangle has all equal sides. So imagine we're rotating it around its center, and we want to take this angle C and make it so that it lands on this angle B. We're trying to figure out how many degrees it would need to rotate. I'm also going to connect A here. How many degrees do we need to move angle C so that it lands on angle B? Keep in mind that a full rotation around a circle is 360 degrees. We're moving it 1/3 of the way around. So we're going to take this 360 and we're going to divide by 3. 360 divided by 3 gives us 120 degrees. So an rotation of 120 degrees will map that triangle onto itself. Or we could go from C all the way to A, and it would still map onto itself. So if this is 120 and this is 120, we can take 120 and double it. We can get 240 degrees. So a rotation of 240 degrees will also map that triangle onto itself. It does not have point symmetry, by the way, because a rotation of 180 degrees would not map the triangle onto itself. Let's go on down to this parallelogram. Put a point in the center and try to imagine how many degrees you would need to rotate this shape so that it lands and maps onto itself. If it helps you to turn your paper, I can't really turn my paper here on the screen, but if it helps you to turn your paper so you can see what it would look like if you flipped it completely over, hopefully you would be able to see that a rotation of 180 degrees would map that parallelogram onto itself. Since you can rotate it 180 degrees and it maps onto itself, that is called point symmetry. So not only does it have rotational symmetry, it specifically has point symmetry. Check out C. Put a point in the center and imagine how many degrees we would need to rotate it so that it lands completely on itself. I guess we don't need to do 360. Three different options here. If we just take this point and rotate it to this point, the figure would land on itself. If a full rotation is 360 degrees, we're going to take that 360, divide it by 4, and get 90 degrees. So a 90-degree rotation will map the figure onto itself. Keeping on going from there, if we started at this original, we'll call it point A and wanted to get to C. That's two 90s put together, so a rotation of 180 degrees will also map the figure onto itself. Similarly, if we just kept going and turning it, it would land on the other corner of the star. 90 plus 90 plus 90 gives us 270 degrees. So all of those different rotations will map the figure onto itself. Since it has this 180 degree option, it also has point symmetry. Try the last one on your own. Try to figure out how many degrees we can rotate this shape so that it would land completely on itself. If you rotate it 180 degrees, it'll map onto itself, meaning that this shape also has point symmetry. There are no other rotations that would land that oval or ellipse, if we're going to be super mathy, onto itself. 360 degrees is true. We could rotate it 360 degrees, but that doesn't qualify for rotational symmetry because every shape can be rotated 360 degrees and land on top of itself. In these final examples, we're going to put it all together. So we're going to identify whether it has rotational symmetry, reflectional symmetry, point symmetry, all of them or none of them. So just remember, point is a type of rotational symmetry. It means it's rotated 180 degrees. Check out the flower. Since we first talked about reflectional symmetry, see if there are any lines of reflection that you could fold that flower on and they would land or map onto itself. Lots of different options here. I automatically see the vertical line through the center. So it has reflectional symmetry. Next, check for rotational symmetry. Could you rotate this flower and have it land completely on top of itself? The answer is yes. You could fold from A to B. Oops, sorry. I'm trying to turn my image. You could fold from B to, we call this C, and the flower would land completely on top of itself. So this has rotational symmetry as well. It does not have point symmetry. So imagine that 180 degrees is halfway around a circle. If we rotated that point A 180 degrees, that flower petal would land down here, and there's not a flower petal down there. So it does not have point symmetry, just reflectional and rotational. Try out the next one. Tell me what kinds of symmetry this shape has. Lots of different options for where you see the line of reflection. As long as it has at least one, it definitely has reflectional symmetry. Because this this star can be rotated at least once and land on top of itself at some different angle. Because the shape can be rotated some angle and map on top of itself, it does have rotational symmetry. It does not have point symmetry because we cannot rotate it 180 degrees and have it land on itself. So just reflectional and rotational. Check out the image of the plane. What kind of symmetry does this plane's image have? Because it has at least one line of reflection, it has reflectional symmetry. It does not have any other line of reflection besides that one. And it does not have any rotational symmetry. I know it could be rotated 360 degrees, but that does not qualify it for rotational. It has to be less than 360 degrees. And if you rotated this plane at any other angle less than 360, it would not map onto itself. So just reflectional. Try out this guy. See what kind of symmetry it has. I don't know if we have enough information to like accurately answer this, but if I told you it's a rhombus, meaning all the sides are equal, then it does have reflectional symmetry. Reflectional symmetry over either of its diagonals. So you could fold it there, or you could fold it there, and it would land on itself. So it does have reflectional symmetry. It has rotational symmetry because you could rotate it specifically 180 degrees, and it would land on top of itself. So it also has point symmetry. Couple more. This wackadoodle shape, are there any lines that we could fold it over so that it would land completely on top of itself? The answer is no. We also could not rotate it any amount of degrees and have it land on itself. So it has no symmetry. Last but not least, our arrow here. See if it has any reflectional, rotational, or point symmetry. Multiple lines of reflection. As long as it has at least one, it has reflectional symmetry. This image, if you took this guy and rotated it 180 degrees, it would land on top of itself. So it has rotational symmetry. And because it's rotated specifically 180 degrees, it also has point symmetry. So all three there. All right. Go ahead and give your homework a shot. I'll be back tomorrow, and we can answer any questions you might have about different types of symmetry. Wish you guys have a great rest of your day.